Hi, I'm Josh.
I'm Stefan.
We did our presentation on acceleration of data management using the power of a GPU.
Here's a list of some terminology that we'll be using throughout this presentation. GPU is your graphics processing unit. CPU is the central processing unit. OpenCL stands for Open Computing Language. It is used for parallel computing, and it's open standard. Cuda is the NVIDIA equivalent of that, which is proprietary to NVIDIA hardware. And GPGPU is a general purpose GPU, which that basically means using your GPU for something that's usually used CPU-wise.
Our next slide is intensive compute tasks. Since most of these have been discussed in class, we'll just list them out here. So we have bioinformatics, signal audio image processing or video, data mining and analytics, searching, sorting, spatial selections and joins, and scientific computing.
We'll now discuss some of the common hardware differences between CPUs and GPUs. The first of these differences is the number of cores. Most consumer CPUs have anywhere from 2 to 8 cores, with some server processors going up to 16 cores, whereas GPUs have many more processing cores, although they are less specified for executive work and better at repetitive work. Another key difference between GPU and CPU is the memory performance. As we can see here, we got an old graphics card, a 580, and an old processor, an i7-260. And as we can see, the memory bandwidth and memory performance is exponentially higher than that of a CPU. And this pattern continues with newer hardware as well. Here we compare a very high-end server processor, which is designed to handle large computational tasks, versus what is considered the most powerful consumer-grade GPU. This GPU is not designed specifically for large computational tasks, and as we can see, the price is about half the amount of the CPU, whereas clock speed is significantly less, although it has an absurd amount of cores compared to the CPU. And as we can see, that translates into a much higher hash rate for the GPU. Hash rates used for cryptocurrency mining, which is highly mathematically intensive. And as we can see, I am highly unlikely to own either of these in my lifetime.
There's also many other differences between GPUs and CPUs. One we already have covered are GPUs have many more simplistic cores with lower clock speeds. GPUs also have more transistors, which are specifically designed to rapidly manipulate and alter memory to accelerate computations. GPUs also have higher memory bandwidths as well, which allows for faster access to data. GPUs also have higher float performance, as well as faster memory, which includes DDR5, which is one of the major reasons CPUs are lacking compared to GPUs. And CPUs have complex cores with higher clock speeds, consumes less power, and for the most part less heat, and the end goal is for low response time and is optimized to execute one task as fast as possible. The pros of using GPUs. GPU is more efficient when the algorithm can be parallelized. It is easier to scale up hardware-wise. For example, with a GPU, multiple can be used on one motherboard, as well as being individual or cheaper for each individual one. Whereas in CPUs, scaling up requires more motherboards for each individual CPU, and the CPU costs more. It is also more efficient when these are true. The algorithm only needs moderate to low flow control, or the dataset is decently large, but still fits within the GPU's memory.
Some of the cons of using the GPU versus the CPU is that the GPU has no preemptive multitasking. The main bottleneck of the GPU is through the PCI bus. This is actually the main bottleneck. GPUs are hard to program for. They have limited memory. Most cards at most have 12 gigs, if that. Profiling and debugging are not easy on a GPU. Another con is data placement. GPU accelerated database try to keep relational data cached on the device to avoid data transfer, which means you are limited to the memory on the GPU.
We have compared both GPU and CPU alone, but what if we were to use both? I mean, we are not constrained to using just one. This is where hybrid querying process engine, or HYPE, comes along. It distributes data operations response time to minimal on both CPU and GPU. It tries to utilize the processing device most suited for an operation while keeping track of the load situation. It only picks the GPU if the algorithm is estimated execution time is lower than its CPU counterpart, including data transfer. This always gets the fastest of the two outcomes.
What does this mean in terms of database management? I'm going to use the example of a binary search, many binary searches to be ran at the same time. As we know, binary search is not that computationally intensive. With a CPU, you would finish one and go on to next, and depending on the data set, it would be pretty quick at hammering that out. With a GPU, we can run multiple concurrently, which in the long run would allow a much faster search. And not just with a binary search, but many other searches benefit from parallelism and the faster memory that a GPU provides. And that's basically what most queries are, is a search for certain information. Here we have a graph of a range query comparison between a CPU and a GPU. Range query retrieves all records where some value is between an upper and lower bound. As we can see, as the number of records increases, so does the time of the GPU and CPU, but we can also see that the GPU time is much lower than that of the CPU time. If we consider only the computation time, the GPU is nearly 40 times faster than the CPU. Here we have a graph of a multi-attribute query with about 60% selectivity for each attribute. And as we can see, the CPU time keeps increasing as the number of records increases, much higher than that of the GPU time. We will now briefly cover the two most popular frameworks used for parallel computing. The first one is Cuda, which is Compute Unified Device Architecture. Initially released in 2007, it was developed and proprietary to NVIDIA, so it only works on NVIDIA software. OpenCL is Open Compute Language, which is an open standard which was initially developed by Apple and released in 2009. Cuda has several advantages over traditional general-purpose computation on GPUs using the graphics APIs. Some of these benefits are unified memory, faster readback from memory, full support for integer and bitwise operations. Also has the advantage of unified virtual memory and scattered reads. This means that it can read code from arbitrary addresses in its memory. Some of the limitations of Cuda include the fact that it does not support the full C library, and it is only proprietary to NVIDIA hardware. Another disadvantage to Cuda is exception handling is not supported in Cuda code. This is due to the fact that the performance overhead would be great with the many thousands of parallel threads running. OpenCL, or Open Computing Language, is also a parallel computing framework. One of the main features of OpenCL is the portability of it, as it is supported on more applications and is truly OS independent. It is also an open standard and open source as well. Some of the limitations of OpenCL include it's very hard to optimize, as many steps are needed for a single program, and is generally considered harder to work with compared to Cuda. Another thing is it is usually outperformed by Cuda, but this is mainly attributed to the differences in the programming model and to NVIDIA's compiler optimizations for Cuda. In conclusion, it's better to use the CPU when your algorithm cannot be parallelized and you need that massive amount of control flow that the CPU offers, and the data set is relatively small. And the GPU is better when the algorithm can be parallelized and the data set is relatively large, but it still fits within the built-in memory of the GPU, and it doesn't require a whole lot of control flow. This has been a brief introduction to using GPU acceleration. It was really difficult to pick the information to include in this presentation. Many of our sources were actually pretty long books written on this topic. It's very wide range. This last slide is just going to include our resources.